Hey everybody, welcome to Supercoding Fun Time with me, Eugene. I'm a professor of chemistry at Florida State University, and this is my excuse to waste time and code fun programming projects on the internet as a sort of outreach event. I haven't done this in a very long time. It's been about a year since the last stream. And tonight I'm lucky enough to have with me one of my brand new postdocs, Dr. Stephen Yuwono. Stephen, say hi.
Hello.
Hopefully, say hi again. I had you muted.
Hello there.
There you go. Okay. So anyway, welcome to Stephen. Stephen's an expert in something called couple cluster theory, which is an electronic structure method that we use in the field of quantum chemistry. I should say that I'm a quantum chemist, which means I'm a theorist. I don't actually do any kind of real chemistry. I just develop theories and models and write computer software for modeling molecules. And so today what we're going to do is go over some of the theory underlying we're chemical engineers. Awesome. So I'm a software engineer, so we're basically the same thing. Anyway, we're going to go through some of the basic ideas underlying some of the theoretical and computational aspects of some wave function methods. And then I'm going to introduce some tools that make implementing these methods very easy. And then Stephen's going to use some of these tools to implement some really cool electronic structure methods. Okay, you guys ready? Stephen, are you ready?
As ready as can be.
Well, I just commented in the chat that I was cold. So I had on a sweater, and now I'm sweating, so sweater comes off. Okay, let's see if I can find the right screen. That is not the right screen. There we go. Okay, so we can scroll up to the top. I just have some notes to go over. It seems like a lot, but it's really not that much. I just have some notes to go over some of the basic ideas for what we're going to talk about today. We're going to be using a technique in quantum chemistry called second quantization, which involves operators that are called creation and annihilation operators. They basically kill electrons, move them between different orbitals that they live in. So the notation we have is for something like the Hamiltonian, which is a central quantity in quantum chemistry. It's the energy operator. You can write this as a sum of these creation and annihilation operators times some integrals. This is an integral involving kinetic energy and electron nuclear potential energy, an integral over these basis functions, phi p and phi q. So this is a one electron part of the Hamiltonian, and this operator just moves an electron from orbital q to orbital p. And then there's a two electron part that describes like electron-electron repulsion, and then it has four of these operators, so it moves two electrons from orbitals r and s to orbitals p and q. And Stephen, you can correct me if I make any mistakes at any time. Actually, don't correct me, because I'll get embarrassed. Just kidding.
I think looks good.
Okay. So the notation I use is different than Stephen's, so if he has any notes, they're going to look different than mine. So that's a bummer. This A hat with a little p is an annihilation operator that destroys an electron in orbital p. This A hat with a dagger, the plus sign here, is a creation operator. It creates an electron in orbital q. This is a shorthand I can use. I could just use the letter p and p dagger. These operators satisfy some very nice properties that let us write down wave functions in terms of them easily. Basically, they have these anti-commutation relations where if I sum the daggered operators in this way, they equal 0. If I sum the no-dagger operators in this way, they equal 0. And then the really important one, well, the non-trivial one, is that p dagger q plus q p dagger equals a delta function. This is a Kronecker delta function where it's 0 unless the labels p and q are the same as each other. And I should note these are creation and annihilation operators for fermions, like electrons. The anti-commutation relations are different for bosons. Okay. So the whole point of using these operators is because it's easy to write down many-body electronic structure methods in terms of these operators. So I'm going to give you an example. There's a very famous theory called couple cluster theory, which is very, very accurate for modeling molecules and electronic structure, but it's insanely expensive, so not terribly popular from applications point of view. Some people choose to use things like density functional theory, but I digress. Anyway, the wave function here, which I have written as psi in a ket, is this exponential operator acting on this reference function, which is usually just a Hartree-Fock determinant. And this operator is written in terms of creation and annihilation operators. So T, the cluster operator, has 1 electron terms, where I move an electron from orbital I to A, 2 electron terms, where I move electrons from orbitals I and J to orbitals A and B, and so forth, up to n-body excitations. Twitch won't let Jay Foley comment. I must have set up the comment stuff wrong. Let me turn off something. Jay, can you try to comment now? Okay, anyway. No, it's Jay's fault. Okay, well, I shouldn't have done that. Shield mode is reactivated, whatever that means. What was I saying, Stephen?
I forgot. I was absorbed.
Okay. So anyway, so the cluster operator has these 1 electron terms, 2 electron terms, and so forth, up to exciting all of the electrons. And normally we stop at some order, maybe moving around 2 electrons. And here, some very important detail is that the labels A and B correspond to virtual orbitals, which are orbitals that are empty or not occupied in the reference function, and I and J and K and L represent occupied orbitals. That's a standard convention. Okay, another case where we might use... I fixed it momentarily, but now it's broken. Okay, so I do have to turn this off. All right. Hopefully now Jay Foley can comment. Anyway, we could also represent other more peculiar or less traditional electronic structure methods based on density matrices in the same way. So my training was in reduced density matrix theory, so that's why we're talking about it right now. Stephen's training was in couple cluster theory. Prepare for deluge, Jay says. Yeah, there's a lot of... This is an info dump for sure. Okay, so I can write down the energy as an expectation value involving the Hamiltonian. If you've taken a quantum chemistry class or quantum mechanics class, this might make sense to you. This is basically the way you connect an observable like the energy of your system to how you would predict a property quantum mechanically. You evaluate this integral, and that gives you an average or expected value of the energy. And we can write down an expression using the second quantized notation for the energy in terms of those integrals I mentioned before, and now expectation values of these operators. So this thing, expectation value of p dagger q, is an element of the one particle reduced density matrix. That's something that's related to the probability of finding an electron somewhere. And this is an element of the 2 electron reduced density matrix, which is the simultaneous probability of finding 2 electrons somewhere. It's so exciting. So anyway, you can write down the energy exactly in terms of these density matrices. So that's 2 very different examples of how these operators show up in quantum chemistry. Okay, oftentimes it's easiest to deal with these operators when you use something called normal order. That's the whole point of this introduction, because the software we're going to use is something that brings these operators to normal order so we can do something useful with them. I can define normal order in 2 different ways, relative to something called a vacuum state or relative to something called the Fermi vacuum, which is, the true vacuum state or the Fermi vacuum. The Fermi vacuum is the Hartree-Fock reference state. So we're going to talk about the true vacuum first. The true vacuum is this empty ket. It's empty. There's nothing there. There's no occupied orbitals. And normal order we define such that all of the annihilators lie to the right of all the creators. So there's always going to be an annihilator, if there is one. It's going to be touching this ket. That means any expectation value of a normal order string of operators with respect to the vacuum state is 0. And you can see that here. This is a normal order string of operators. The creator is to the left of the annihilator. And if I annihilate nothing, I can't do that. So this is equal to 0. This is an expectation value of 2 creators. A creator acting to the left acts like an annihilator. So I can't annihilate this bra state. So that expectation value will also be 0. And then similarly, this expectation value would be 0. Okay? So defining the vacuum allows you to identify what terms are 0 easily. So let's take this operator here that's not in normal order and express it in normal order using those commutator relations, anti-commutator relations I listed a few seconds ago. Q p dagger is equal to this delta function minus p dagger q. This is now in normal order, and this is just a direct delta function. It's also in normal order because it involves no operators. And if I take the expectation value of this thing, there's 2 terms. Expectation value of the delta function and expectation value of this guy. And I just argued that this is 0 because it's a normal expectation value of a normal ordered operator with respect to the reference function. There's 9 very brave souls still in this stream. How exciting. Okay, so expectation value of a string of operator with respect to the vacuum state is trivial to determine. All you have to do is bring the state to normal order, and then the only terms that survive are these ones that are called fully contracted that don't involve any operators. So up here, this one doesn't involve any operators. It's the only term that survives. Steven, have I made any mistakes yet?
I think so far so good.
Okay, great. That's why Steven's here, to double check me.
I'm watching you on my phone, so like.
Oh yeah,
super
because
small.
Steven, we have a very janky setup here. Steven's video is fed to Twitch through Zoom, but he can't see me except for on the stream. And then his audio is coming through Discord, and he's going to share his screen through Discord later, God willing, if it works. Okay, fingers crossed. All right, so now I'll give you an example, and then we'll bust out the code that does these manipulations. So in these V2RDM variational 2-electron reduced density matrix methods that I haven't really discussed, it doesn't matter, but I'm going to explain some things about them. You express various conditions on this 2-electron reduced density matrix. I'll go back. So I wrote down the energy in terms of these 1 and 2 RDM before. And in these 2 RDM theories, we try to say, okay, I don't want to use a wave function. Instead, I just want to deal with these density matrices. And so I try to find the elements of the density matrices directly without a wave function. But the challenge is it's very easy to find a density matrix that could give you a good-looking energy, but it doesn't actually correspond to a wave function, and you have to impose a bunch of conditions on it. So that's what I mean here when I say there's different conditions in 2RDM theory. There's some 2-particle conditions where a bunch of matrices have to have non-negative eigenvalues. The 2RDM, a 2-hole matrix, which tells you, if this tells you the probability of finding 2 electrons, this tells you the probability of not finding 2 electrons in 2 places. And then a particle hole RDM, which is a simultaneous probability for finding an electron and not finding an electron. And all of these things should be positive because they're all related to probabilities, and probabilities can't be negative. It's as simple as that. These are the elements of these RDMs. I have the one I already defined for you, and then this Q2 and G2 just have different orders of these operators. And in an actual calculation, you have to not only enforce that these are positive matrices, but also that the elements are related to each other in the correct way based on the commutation relations of these operators. So the point here now is I'm going to try to derive an expression for G2 in terms of D2 based on moving these operators around. Okay. In order to do that, I just need to bring the operator that defines G2 to normal order, which is pretty easy to do because it's not a very complicated looking string of operators. So I have this matrix element is P dagger Q, S dagger R, and I can rearrange that by switching Q and S with delta QS minus S dagger Q. And then I end up with these operators. This is in normal order. This is in normal order. And now I go back and take my expectation value, and I see I have an expectation value of this guy, which gives me my 1 RDM element, and an expectation value of this guy, which gives me my 2 RDM element. I should scroll up because Steven's head is in the way. Okay? So we just use those commutation relations to define the relationship we expect between the particle hole matrix and then the particle matrices. This was very easy to work out, but you could imagine if you had RDMs defining 10 electrons instead of 2 electrons, these types of manipulations would become very, very tedious. And it ends up being perfect work for a computer. So now, as this implies, we should insert a demo of some software that my group has developed to do exactly these types of manipulations. Whew, this is exhausting, Stephen.
Wait until I started
I can't
implementing.
wait. I hope you have diagrams. It's going to be amazing.
I will do the notes live.
Oh, nice. Okay. Even better. So I opted not to do that because I would spend 4 hours just going through the notes. Okay. So I'm going to use this software called PDaggerQ, which is spelt out in this very silly way. PDaggerQ. It's free. It's available on GitHub. You can download it. It's pretty easy to install. We'll even install it live. There's pretty good documentation. You install, it's a C++ library, but the interface is all Python, and you can just install with either a setup script or pip install. If you are a developer and you wanted to modify the code, if you modify the C++ code, you just have to do some additional commands. And then there's a bunch of examples here, and all the different awesome operators and functions we've implemented are outlined. Cool. PDaggerQ. All right. Let's download this. So I have a terminal here. I'll get rid of my notes for the time being. And I may have foolishly chosen a color that exactly matches my background. Yay, pip install. That's right. It's super easy, Jay. I don't know if this is Jay Foley. He's a professor at UNC Charlotte. Jay, I don't know if you've ever used this code. It's super fun. You should try it. Okay, so I have made a Conda environment for this project that I load as such. Really, all you need is Python. So there's some other stuff here for some other projects, but this is basically just an environment with Python 3.10 or something like that. I'm going to go to software. You did, in fact, use it. Excellent. Software. I don't need to show you all this stuff. Oh, my God. Oh, my gosh. There's no clean? Clean not found. How can there not be the function clean? This is a new build on this computer, by the way. I'm on a Linux box, so it's a miracle any of this is working. Okay, well, I'm just going to clone the repository. Go into the repository. There's the README that we just went through. If I want to install it, I just say Python setup install. So it has to check some C++ stuff. It builds all the C++ machinery. It complains about some things. And then we cross our fingers that it actually compiles. It did. Great. There's an examples directory, which has a gazillion examples in it. And there's one example called RDM mappings.py. So I'm going to open that one. I'll make this a little bit smaller so that it all can fit on one line. And I'm going to delete all the ones that we don't need. So in that example, I just wanted to do the mapping between the G matrix and the D matrix, and I should call this G2 and D2. To run this code, well, basically what this code, oh man, I deleted too much stuff. Wait, yeah. Okay. This is so not necessary, but here we are. Okay. Is there anything in PDaggerQ that really needs to be C++ for performance reasons? Probably not. So actually, this code is not very efficient. Most engines that derive equations the way we're doing this use something called Wick's theorem. and you don't need C++ to do Wick's theorem. You can do it in Python, and it's very fast. My code is not smart. It uses these commutator relations that I just introduced to you, and so it's way less efficient than a Wick's theorem engine. So from that point of view, yeah, it probably should be C++ because it's doing a lot of work. I imagine a Python version would be much slower, the way I've implemented it. Great question. Thank you for making me look dumb. Okay. I think we used P, Q, R, and S. No, S and R. So, okay. The first thing you do is you need to import the library, and then you define a PQ object, which is actually a PQ helper. And you see this helper takes an argument, and this argument here is true. That means I'm defining normal order with respect to the true vacuum. And then anything I want to add, the base way to add operator strings is with this add operator product. As I'll show you in a few minutes, there are much more complicated functions, but they all end up running through add operator product, so you could implement anything you want with add operator product. And so what this does is it says, okay, I have my true vacuum, and I have a string of operators where I have a factor 1.0, and then a creation operator with the label P, annihilator, label Q, creator, label S, and annihilator, label R. I've used stars to denote the adjoint or the dagger. And then so this adds the string and brings everything to normal order automatically. And then simplify will go through and delete terms that should be 0 or should cancel or should be consolidated. And then I can print. And so this print takes arguments, optional arguments. I can say string type equals all, and that will print all of the strings, even if they're not the fully contracted ones. You could also say print string type fully contracted, then that would only print the fully contracted ones. And then there's a clear function in case you wanted to do something else afterwards. Okay, let's see if this works. Python, RDM mappings. Okay, so now let's bring this guy back. Perfect work for a computer. Okay, and I have GPQRS is equal to D1PR, so that's P dagger R, with a delta function, DQS, minus D2PSRQ. And so that's PS, and the Q and the R are backwards because that's just convention. So the computer code derived exactly what we did. And this was a very easy example. Cool. Okay. Moving on. This case was very easy. We were able to work it out by hand, but as I said earlier, it becomes much more tedious to do this with higher particle levels. So again, it's perfect work for a computer. We already did the Python demo. Okay. RDM theory is fun. Yes, it is fire or lit or something. Okay, RDM theory is fun, but most people who would want to use this package, which is basically my group, would want to use this for wave function theories. And the real utility here is it tells us what integrals over second quantized operators are non-zero. So as an example, I'm going to use coupled cluster theory with double excitations. So I have the same. I need to make sure I can see my OBS window. I have the same wave function I defined before, but T is simpler than it was. It only has these double excitations in it. And I take the Schrödinger equation. This is the energy equation, the eigenvalue problem for the Hamiltonian. I know the Hamiltonian. I want to solve for the wave functions and the energies. I insert my coupled cluster wave function. And then in coupled cluster theory, the way you solve this is in a projective way where you left multiply everything by e to the minus t. And then that makes these guys go away. E to the minus something times e to the something is just 1. And you're left with this pretty weird looking expression for the energy, E minus T H E T. What's the special name for this Hamiltonian, Stephen?
It's the similarity transform Hamiltonian.
It's a central quantity in coupled cluster theory.
Indeed. And it is not Hermitian.
It is not Hermitian, which is very weird because your Hamiltonian should be Hermitian. What are you going to do? You're just going to
break it.
You break it. But it doesn't really matter if you don't truncate your cluster operator. But here we here we truncated the cluster operator. So there could be problems based on the fact that this thing's non-Hermitian. Like you could get an energy that's not physical. Anyway, let's forget those problems. The question now is how you evaluate something crazy looking like this. And the answer is to introduce this BCH expansion, which makes things look even crazier, where this similarity transformed Hamiltonian can be written as the Hamiltonian plus commutators, a single commutator, a double commutator, a triple commutator, a quadruple commutator, and so forth. That doesn't seem like it would be very useful, but it's hugely useful because the BCH expansion stops at 4 commutators in couple cluster theory. Well, if you're trying to evaluate the energy, the wave function. Okay, naturally truncates at 4 nested commutators. So for the energy, it actually turns out it truncates very quickly. Anything after the single commutator is 0. So the energy expression looks like expectation value of that first term plus a commutator involving T2. So I have HT2 minus T2H. That's the definition of a commutator if you haven't taken a quantum chemistry class. I don't know why you'd still be in here if you hadn't taken a quantum mechanics class, although it is fun. Okay. I hope there are people who are non-experts, and I hope they ask questions looking at the chat. Okay. So I have these 3 terms. This term is just the energy. It's an expectation value of the Hamiltonian. It's the energy of that reference state that I'm calling 0. These 2 terms, I can look at this one and see that it's actually 0, because if I expand T2, I have this sum and these operators. This is a creator of a virtual orbital, but creator acting to the left acts like an annihilator. So this is trying to kill an electron in an empty orbital, because the virtual orbitals are not occupied in this 0. So that will be 0. That means this whole expectation value is 0. You can see that here. I say this guy is the same as A without the dagger acting on 0 with the adjoint taken. So now you can clearly see this is an annihilator trying to annihilate an electron that's not there. And then that gives you 0. So that's useful. Now our energy expression just has these 2 terms, the energy of the reference and this other thing. This is where it gets crazy. If I tried to do this by hand, this would be a complete nightmare without the fancy diagrammatic techniques that Stephen knows and I don't really understand. This expectation value, I'm going to expand both the Hamiltonian and the T2 operator, and here we are. We have 2 different terms. There's a term involving the 1 electron part of the Hamiltonian and the 2 electron part of the Hamiltonian. And you have these insane looking strings of operators. We could evaluate these monstrosities by bringing all of these operators to normal order, and only the fully contracted terms would survive. But this thing is not the true vacuum state. That's how we were talking about normal order before. So we need to think about all the operators that define this state. That reference state is defined by a whole bunch of creators acting on the vacuum. So this is a product of a bunch of creators. And so if I want to think about normal order with respect to the true vacuum, I can't forget about this piece. So number 1, the string we're dealing with is much bigger than just the individual operators from H and T2. And number 2, the overall string is system dependent, because it would be different for a system of 10 electrons or a system of 20 electrons because this product is different. So the solution here is to change how we define normal order and use normal order with respect to the Fermi vacuum, which is that Hartree-Fock state. Okay. There are very simple rules for doing this. Rule number 1, any operator that annihilates the reference is designated as an annihilator. So if I take a creation operator and try to create an electron in an already occupied orbital, that can't happen because I can only put 1 electron in 1 spin orbital. So that gives me 0. That's an annihilator. And if I try to annihilate an empty orbital, that will also give me 0 because I can't destroy an electron that's not there. So these are both annihilators. All other operators are designated as creators because a dagger acting on 0 the reference is not necessarily 0, and I acting on the reference is not 0. Cool. So normal order is defined in the same way it was before. All the creators have to be to the left of the annihilators. It's just we've changed the definition of what the creators and annihilators are. There's a very annoying feature here, especially when you're trying to write a code to do this. Any sum that has general labels, occupied and virtual orbitals, has to be broken into sums of occupied and with occupied and virtual labels. So the Hamiltonian, you have to break it up into a bunch of different terms. But once you do that, then you can evaluate integrals in a very simple way. So here's an example. This is just the expectation value of the 1 electron part of the Hamiltonian with respect to the Hartree-Fock reference. So like I just said, you have to split this sum into a bunch of sums over occupied and virtual labels so I can actually know what labels are the creators or the annihilators. So I have split it into 2 occupieds, an occupied and a virtual and an occupied, and 2 virtual. And 3 of these are immediately 0 because I know that the operators are already in normal order with respect to this function. And one of the key tenets of all of this is that an expectation value of a normal order operator is 0. Yep. Okay. So you're just left with one term. This operator is not in normal order. So I bring it to normal order using those anti-commutation relations from before. I have 2 terms now. I insert those. One of them has a delta function. The other one's 0 because it's an expectation value of a normal ordered operator. And now I have an expression where only this term survived, the fully contracted term, and I know that the expectation value of the 1 electron part of the Hamiltonian is just a sum of the diagonals of this matrix of integrals. That was so easy. But you could imagine that it would be much, much more complicated if you had to evaluate something other than just that simple expression I gave you. So now, the example. Couple cluster doubles. Here is my energy expression, the reference energy, and then these other bits that we need to bring to normal order. There's no way I'm doing this by hand in this demo because it's super tedious, but it's perfect work for a computer as before. So let's do that real quick. Okay. I have a code for the energy from CCSD. It looks very similar to the code I had before. I have import pdagger_q. I grab a pq helper, but this time the argument I pass to it is Fermi, because I want to use the Fermi vacuum instead of the true vacuum. And then I want to evaluate this thing. That's the energy expression. There's an operator there's a function that we don't need right now, but I'll go ahead and introduce it to you. You can define strings of operators that define your bra or your ket state with these set left operators and set right operators. There is nothing here other than the reference, so this operator is just 1. This is not necessary to have there. I'm not sure why it's there. If I want to do the 1 electron part, I use add operator product. There's actually a specific function that uses that defines the similarity transform itself, but we'll do it explicitly in this example. So I have my 1 electron part. That's the Fock matrix in the language I'm using here, so it's F. And I have the commutator of the Fock matrix with, this isn't CCD, this is CCSD. So let's change it. Let's get rid of all the T1s that are everywhere. Okay. I'll give myself more. So I have the 1 electron part, which is just this Fock operator. And then I have the 2 electron part, which involves a commutator of the Hamiltonian with T2, and the 1 electron part of that. So commutator F and T2, that's this add commutator function. And then there's so that's the entire part of the 1 electron part we need to worry about. Then there's the 2 electron bits that involve this thing V, which is the fluctuation potential. It's the 2 electron part of the Hamiltonian, and it has the part that's just the operator itself, and then the commutator with T2. So each time you call one of these functions, it adds a bunch of operators and brings them all to normal order, and it accumulates them as a list. At some point, you might want to say, okay, do any of these terms in my list cancel? That kind of thing. So you call the simplify function, and then you can call this. I'm using a different function here. I'm calling fully contracted pq.fully contracted strings. This will give me a list of all of the fully contracted terms, the ones that are non-zero, and then I print them. Then I call clear. I could do more work after that. Okay. Save. Python CCSD energy. And this is what I get. I see there's three terms here. This term plus this term, it turns out that's the reference energy. That's the Hartree-Fock energy. You can't see it. It's behind my head. That's the Hartree-Fock energy, and then the only part beyond the reference energy involves this contraction of T2 with the 2 electron integrals. So that hideous expression here, there we go, boils down to these three very simple looking equations. How fun. Okay, last example. If you wanted to evaluate the wave function itself, you'd have to solve the CCD cluster amplitude equations, which you get to in the same way we got to the energy equation. We take Schrodinger equation, left multiply by e to the minus t, but now instead of left multiplying by the reference, you pick a doubly excited determinant, which is behind my head. You pick a doubly excited determinant, and I realize my mouse must be really small because I can't see it. And then that gives you an expression. This thing is equal to 0. And that defines an equation that you solve to determine this amplitude. We're not going to do that because I've talked too much in Stevens terms. So let's do that example real quick. CCSD. So here it's the same thing. I have a PQ object. Now I want my left state to define that excited amplitude. I'm using ij, a, and b here. I can change my notation to match that. So I have ij, b, a, ij, b, a. So here, this set left operators defines this string of this. This is shorthand for a string of creation and annihilation operators where there's 4 of them and the first 2 have daggers. So that tells the code that this is the bra. And then we're going to do this a little bit differently. I'm going to say add st operator. Well, this is a perfect opportunity to look at the manual. How do we use add st operator? Okay, so add st operator, I need to say a constant I multiply it by, and then the operator I'm similarity transforming, and then the things that go in the exponent. That's easy enough. I'll just copy that. And we're just doing CCD, so we don't need T2. And oh my goodness. See, there's all sorts of... I guess I should have gone over this. For solving the doubles equations, there's more commutators that show up than in the energy expression. So I had done this all by hand in this example, but it's easier to do it explicitly with the add st operator. Oh my gosh. Function. And so I have Fock operator and fluctuation potential. And now I just say Python ccsd doubles.py. And it spits out all these expressions. That's the full CCD doubles equations. So you have here, there's an element of the Fock matrix and an element of the T2 cluster operator. And we use Einstein notation, so repeated indices are summed. So this K is a summed label. And then this P represents a anti-symmetrizer. So there's actually 2 terms here. One that looks like this, and another where you switch the I and J and have a minus sign. And that's it. You know how long would it take to drive that stuff by hand? Steven, I know you've done this before.
Too long.
Too long is the answer. Okay, so that's my introduction to the software that Steven's going to use, and I'll hand everything over to him unless, Steven, you want to add anything? Nah, I'll just hand it over to you. Okay, so now we get to see if how hard is it to add a new operator to PDaggerQ? It depends on what the operator looks like. If it's just like I don't know, that's an involved question. Probably pretty hard. But it's already got a lot of, I can't think of any operators that it needs. It's got 1 and 2 electron operators, and you could define a 3 electron operator, I guess, using the existing tools. But actually going in the C++ code, it's pretty ugly because I wrote it.
Yeah, I can actually also like generate like intermediates for couple cluster equations, for example, in a very hacky way. But just by defining proper creation or annihilation operators on the right and left, then putting in the @st operator that you want, you can create all kinds of crazy diagrams or terms.
Yeah. So that's a really good point. With the add operator product function, you can do anything. The add st operator cleans things up for you, and then like Steven just said, okay, so here are the built-in operators. 1, that's an interesting one. 1 body operator, 2 body operator, specific forms of 1 and 2 body operators, Fock operator and fluctuation potential. And then, like Steven just said, you could define any operator you want as a collection of these creation and annihilation operators. And then there's also built-in up to quadruple excitations. So T1 through 4, L0 through 4. This is for equation of motion couple cluster that we're not going to get into. There's add commutator, add double commutator, up to quadruple, and then there's add st operator that does that for you. Does the whole BCH expansion up to 4. Yeah, set left and right operators, and so forth. Check it out, it's fun. All right, Steven. Are you ready to share your screen?
I guess. All right, let's do this. Don't judge me. Wait, actually.
Hold on. I have to address the chat. Thanks, Beaker Overflow. I am also glad that you're here, although I wish I knew who you were in real life. Glad you made it nonetheless. Blue density. Would this work for working with operators that use anti-commutators? You can define the anti-commutator yourself with 2 add operator product functions. And actually, adding an anti-commutator function would be very easy, as you just call the add operator product function twice. Maybe, Steven, once you get through CRCC, we can do an add anti-commutator function.
Ooh.
Danny! A blast from the past. Danny Gibney was an undergraduate with me. He was awesome. And then he went on to University of Chicago for a PhD with David Mazziotti, which is where I got my PhD. So now he's an RDM guy. Danny, you should use this code. Cool. Okay. All right. Have you shared your screen?
I think so. Yeah.
Okay, there it is. There was a way to hide this stuff that I can't remember. View. Do you remember how I did this yesterday?
No, because I couldn't see your screen yesterday.
Oh, right. Oh, this is so upsetting.
That's fine.
It's
Wait until
it's
we go to the part where I code live. That would be upsetting.
it's just kind of small, is all. I guess you can make your font bigger if you need to.
Yep, I can do that.
Oh, 49ers guy says couple cluster theory is better than RDM theory. I gotta tell you something. Steven and I have a very strong opinion that couple cluster is an RDM theory. And I once heard Piotr Piechik say that in a room full of people at a conference, and he knows what he's talking about.
Yep. So Piotr Pichu is my PhD advisor, and he also said in a room full of his group in a group meeting where he was grilling me for giving a presentation on couple cluster RDM, and he was like, you know what, couple cluster is more closely related to RDM theories than wave function theories. And then was like, I'll let you think about it. Took me 1 year of postdoc with Eugene to finally figure it out.
Now you believe him. Oh no, what have I done?
All right. So, okay, we kind of have, I guess like the scope kind of grew since we planned this, but we originally planned to do like an extension of the examples inside PDagger Q to OpenShell, and then we're also planning to do CRCC to Tree live. We'll see if that works out or not. Most likely it will not. But the code will be there, and you will be able to see the working equations generated from PDagger Q. So I guess we'll first go with the extension to OpenShell, which I cheat because I already did it, and just to make sure it works. But we can look at the current infrastructure.
So maybe.
Okay.
Well, I guess I won't interrupt you. I was just going to say, in the examples folder, one thing I didn't mention is that there's interfaces to Sci4 and PySCF that use PDagger-Q generated code. The outputs I showed you guys only generated equations, but you can also generate the code itself.
Yes. So if you go to the examples directory under the root PDagger-Q, then all examples which has code gen, they will give you working equations and codes. All right. So for example, if we do that, look at that, einsum. And it even gives you the function header and whatnot. All right, so if we go to the Cipher interface, and if you look at the CC example, we'll see that basically all the examples are right now closed shell, right? So we want to make sure we can do this for OpenShell. So, okay. If we look at how, sorry. If we look at how this thing is run, so for example, this is interfaced with Sci4, right? And you can see that first got to import some stuff, import Sci4. So I'm in a Conda environment that already has Sci4 installed. And then basically you just import all the codes. That's what you need. So first you can see that you initialize, in this example, a molecule, give it a geometry, in this case it's water. So you give it the option spaces set, Hartree-Fock, convergence criterion, and SCF type PK, which means do like explicit integrals, right? Don't do density fitting or Cholesky decomposition. And then give that option to Sci4. And then you basically just call this CCSD function, which, as we see here, lives in CC tools. Right. So I'm just gonna work with CCSD for now. But now let's take a look where CCSD lives in CC tools.
I hate to interrupt you, but it's doing that blurry thing again.
Okay, should probably close some stuff so that it's not eating resources.
If
Maybe
anyone
that
knows how to get Discord to not throttle your upload speed, that'd be super. Blue density, what is import number? What's number?
That's Marcus. So number is
I have to write this down.
that's a tool to uh, basically parallelize your Python codes. Yeah, for anyone else watching, Marcus is a group member. He is a computer whiz. So you should listen to him when he gives you suggestions about coding practices. All right.
Rain,
Is it still?
Rain is here. Rain's a research faculty in my group. She says her screen is frozen, but mine seems to work on my laptop here.
Yeah, it's probably my internet quality. I'm sorry.
That's okay. Do you know any jokes?
My internet speed.
Haha! That's pretty good.
All right, well, I just restarted sharing.
Yeah, it looks
That
great.
works. All right. Okay, so this is the CCSD function, right? Anyway, we're not gonna use number today because I haven't learned how to use it properly. I just have to add a decorator on your functions, but that's for another day. Marcus, you can do a stream on how to use number. Speed these things up. That'd be fun. Okay, anyway, so
agree.
CCSD right now is done in the spin orbital basis, as you can see on this flag. Or that's the default. You can always turn it off. But the way it's currently set up now is that all of this function assumes that the number of, like if we go to this get integrals function, which is where we should go, I guess. Oop, oop, where's get integrals? Here you go. Yeah, so you only have one variable assigned to it for NO, which is number of occupied orbitals, in this case, doubly occupied. And then basically, yeah, you assume the same number of alpha and beta electrons, right? So we kind of want to generalize that. In fact, if you go down a little bit, the infrastructure already exists with the spin traced or spin integrated code, where now you can see like, oh, we have slices and basically numbers of alpha and beta electrons treated separately. So we are basically just gonna build that infrastructure and just plug it here. All right, so as I said, I kind of cheated because I already did that. So let's look at an example. Boom. All right. So yeah, I don't know if it's a good way to do this, but sorry. Get integrals. There you go. All right. So now, yeah. So as you can see here, the get integrals function, I basically just add another variable, or I split the case. Now we have NOA and NOB, which is grabbed from the wave function object from Cipher, and N alpha and N beta is the number of alpha and beta electrons. Right.
You're blurry again. And also, everybody seems to be on board with a demo from Marcus. So, good job.
Nice.
Committing him to that.
Oh, is it blurry again? It is blurry again. Man. Okay. Yeah, I'm not sure how I can make sure it's not throttling.
Just you could just stop sharing and reshare again. That seemed to work, right?
Man, this is gonna be more painful than I thought it was
I
gonna
think
be.
you're doing this on purpose so you don't have to do CRCC.
I think so. Or the computer is helping me do that. There you go. Looks okay right now?
Yes.
Cool. All right. Then, okay. Continuing from where we were. So now because we have different alpha and beta orbitals, so of course your number of virtual alpha and virtual beta has to be adjusted, and you just do that, right? Yeah, these two are actually never used, so I just commented them out
Perfect.
in the example. Like, I think the CCSD code will grab the epsilon from the fog matrix, just grab the diagonals, right? So we don't actually need to do that. All right, so now what is important here is to also grab the alpha and beta MO coefficients. So if you look at the vanilla Pythagore Q, you just grab the alpha, which is fine for closed shell, and the beta will be identical, right? So you just do the transformation with one matrix, basically. But now we need to separate the cases into alpha and beta. Grab the Cyforce, molecular integrals helper, and then we basically need to construct the different blocks, the alpha and beta, and alpha alpha beta beta for two-body integrals, and so on and so forth. Yeah. So basically, for the one integrals now, so it has two indices, right? Each PQ. Now they have to carry both. Both can either be alpha or beta, right? You can't have integrals that couple alpha and beta in your Hamiltonian, unless you do some fancy spin flip Hamiltonian.
Or if you
this
have
is not the case.
spin orbit coupling. But this
Or
is
if you do spin orbit coupling.
non-relativistic.
Yes. And then this will unpack these electrons, which are defined in terms of molecular or spatial orbitals, right? And into spin orbital basis. So we'll look into how we are modifying this. But after that, you just do the same thing with the two electron integrals. You have to get the proper alpha. And so now we have electron 1 alpha, electron 2 alpha, or electron 1 alpha, electron 2 beta, or both electrons beta spins. And I believe with Psi4, you do this in chemist notation, which means that this is electron 1, and this is electron 2. So you can have, just, I guess if you just play around and like, whether it's going to be chemist or physicist notation, just plug in whatever notation you think it is, and if it gives you the wrong number, it's wrong. Again, and then you just plug it into this function, which will unpack two electron integrals from spatial or molecular orbitals to spin orbitals. And then you got to antisymmetrize your two electron integrals. And basically, from then on, it's pretty self-explanatory. You just now your fog is determined in terms of this new proper blocked integrals, and you just return the objects. Then you just run it, right? So now we can look at the how we unpack these functions, because if we look here, let's see.
You're blurry again.
Okay. Well, that was a perfect segue because I was changing screen.
Intentional again.
Almost done with the open shell. Now we'll just run an example and then we will go to CRCC. Or at least I will generate the working equations for the CRCC, and we can try to build the driver and see if it actually works. Right. Anyway, so now you can see here that in the original function, when we are getting the one electron integrals in terms of spin orbitals, you only need to fit in the one electron integral in terms of in MO basis, the number of spatial orbitals, and the number of occupied orbitals. But now we will have to switch this to in terms of different slices of alpha and beta, right? And here you can see there's a logic which basically go through from like first orbital to the very end, right? Number of spatial orbitals, and you will blow up this one electron integrals in terms of MO to something that's doubles in its axis, so like 4 times the size, because we have twice as many spin orbitals as spatial orbitals, right? And there's a logic that checks whether your index is in the alpha or in the beta range, and then you assign at the end of the day the proper blocks based on your spatial orbital. Now, in our case, now you can see that, I'm putting in more information here. I'm putting in the alpha block, the beta block, the number of spatial orbitals, and then the number of occupied alpha and beta, right? And then if we go to where we are working on this, right. So basically now I'm going to make slices, right? And so slice, if you slice is a type of Python object. If you put it inside like an index, then it will give you the proper range. For example, in this case, I say SOA, which means spin orbital alpha. Then it goes from 0 to NOA when you put it here. So it acts like a slicing of a list. And so I just basically defined new slices in terms of alpha and beta occupied and virtual indices. And now the shape of its axis now is going to be ordered in this way. So this is also something that different codes handles differently, right? I know there are codes that do like alpha beta alpha beta alpha beta and then just go in order of spatial orbitals. So that kind of corresponds to like your usual MO picture, where it's just energy ordered and you have alpha and then beta, alpha and then beta. In our case, I just tried to stick to the existing infrastructure for easier or less modification. We will have first the occupied alpha, and then occupied beta, and then virtual alpha, and then virtual beta. Right. Wait, am I blurry again?
Yep.
Okay, I can see that the stream was blurry. There you go. It asks me for a feedback every time I stop streaming, so I guess I can give that feedback, and then they'll say like, your internet connection sucks. Anyway, so now you can see here that the slices work in this way, right? So my spin orbital will be spin orbital occupied alpha will be from 0 to number of occupied alpha, and then the next slice is for spin orbital occupied beta, which starts from NOA to NOA plus NOV. And then now these two slices combined together give you the occupied slice. And then you just continue building according to the order that I just explained, right? Now that's the ordering in the spin orbital basis, and then I also have the corresponding slices in the spatial orbital basis. or MO basis. And basically I just map from the proper block, and I have to grab, for example, if I'm working with the alpha block, then I will grab the proper, slices from the alpha block. And when I'm working with the beta block, I will grab the proper slices from the beta block that I built. And you can see that, as we said before, I will not be populating like cross terms that has alpha and beta, that has different spin in the slices, right? So those blocks will stay 0, because I'm not gonna worry about relativistic effects.
Not yet. That's the next step.
Not yet. At least not here. I do in the work that I'm actually doing. So now for the 2 electron orbitals, so I have basically the same idea, right? Like, just make sure you have your spin orbital slices and your MO basis slices, right? And it's defined in the same way. But now, if you think about it, we have 4 indices that we have to worry about, right? And if you think like, well, okay, now Stephen's gonna like explain forever, like all the alpha, 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 alpha blocks, alpha, alpha, beta, beta blocks, and so on and so forth. I was thinking about it when I wrote this, and I was like, no, that's gonna take too long. And for some reason, it dawned on my mind that, the slices are either occupied or virtual, right? So you can think of them as binaries. It's either going to be 0 or 1, where 0 is assigned to occupied and 1 is assigned to virtual. And if you think about it, all those slices are basically just binary representation of your numbers. Or, like you can make a binary number that has 4 digits, right? So you go from 0000 to 1111, and they will correspond to, and if you, so that corresponds to integer going from 0 to 15, right? And
wait. Now that it's blurry again.
But this is the cool part. Okay.
That's why it's been blurry for a minute, but you weren't moving around yet.
Okay.
I knew it was going to get cool. Oh, yes. That's a great idea. Is this ready to be pushed to?
Kinda.
Because then, if it gets blurry, they can look at it on their own, even when it's blurry.
Yes, I will. I think. Yes, this should be fine. I have some other functionalities, which is like I already started with CRCC, so there are some trash, but I can clean it up and push it.
Well, it's not blurry now.
Wait, it's blurry again?
No, it's not. So
awesome.
Can you explain? All right, so what are you doing?
Right, so basically I want to grab like, okay, so in the one body integral, you only have 2 indices, right?
Yeah, no,
it's
I just wanted you to explain the 2 lines for I and then the PQRS equals.
Yes, right. So the reason I'm doing this is because so now we have 4 indices where now we have different cases, right? Like all these 4 indices you can have occupied or unoccupied. So if I just write everything explicitly like how I did before, then I will have 16 lines for each spin block. So now instead of doing that, I represent my occupied and virtual slices as 0 and 1s. And you can see here that I go for I in range 16, which means I will go from 0 to 15. And if I convert the integer 0 and up to 15 to binary, which is defined using this little function here. So just return 4 digits in binaries, right? I will get 0, 0, 0, 0, and then 0, 0, 0, 1, 0, 0, 1, 0, and so on and so forth until 1, 1, 1, 1. So this gives me basically like, all the slices that I need, from all the way from all 4 index being occupied to all 4 index being virtual, and everything in between.
I had no idea that there was a print format to print an integer in binary.
Yes, there is this B. Prints in binary is so awesome. So actually for the one body, I could also convert it. So I will go from 0 to 4. 0, 1, 2, 3 actually, right? Because we need 4 blocks. Like OO, OV, VO, VV.
Yeah, that's fun.
Yeah, so this is just something which we might also do in some other session probably, because I also implemented symmetry. And you know what's fun with symmetry? Eugene knows. You can represent irrep products using integer XOR operation. The binary, yes.
That's the most amazing
It's amazing, right?
trick. I love it.
Yeah. So yeah, we can use that to basically get.
It's because XOR is an abelian. It forms an abelian group. It's so cool.
It is. It's so mind blowing. Like you can map. Yeah. You can map like a binary operation into like group theory. It's awesome. Anyway,
your screen's blurry again.
Okay.
I still haven't figured out how to get rid of this junk at the bottom.
Well, you know what? Next time if we're doing this, I'll probably just stay in the lab and we can rely on FSU's gigabit internet probably, assuming they're not doing maintenance. Anyway, so now PQRS is just a bunch of zeros and ones, right? Because I use this fancy little generator, fancy for me, and then you just grab the proper slices from this mini tuple. It's either occupied or virtual, right? And you just assign the proper spin block to the large to the 4 object. So you have the alpha alpha case, the alpha beta, beta alpha, and beta beta case for the 2 electrons. And then you just return the objects. So that's how we deal with basically generalizing this to open shells, right?
Cool.
So,
Very cool.
Yep. So now I have created this example with open, just basically just the example and script, and I just copy it over. And this is our beloved magnesium fluoride molecule. And now you can see the charge is 0, so it's neutral, but the spin multiplicity is doublet. Ooh. Okay, someone's gotta go.
It's Danny. Bye, Danny.
Right, so now, because it's a doublet, it will not have the same number of alpha and beta electrons.
Marcus had a suggestion, but it involves turning off hardware acceleration.
Ooh. Okay, how do we do that?
Oh man, there's a delay on the chat. So there's a delay when you ask him the question, then he hears it. Oh, there it is.
Under video and audio. All right. Okay, well, we can try disable hardware acceleration.
Did you find it?
All right.
He gave you a different suggestion.
Yeah, I did see that in Discord.
Well, it's not
Well,
blurry.
yep, I did disable it, so hopefully it will stay crisp. So far, yeah, I think right now it's not blurry, right? Awesome. Anyway, yeah, so this is CCSD energy I get from just running pure Psi4. And so we'll see. And actually we'll see a bug, so we can open a ticket.
Is it a bug in PDaggerQ?
No, it's just in the example.
Oh.
I mentioned it. Yeah. And we will identify where that bug is. So awesome. I'm just trying to add content in the stream.
No, that's great.
All right. Well, so right now we will do two things, and as I mentioned, so when we use spin orbital basis true, so it will now call all the new functionality that I just added. And if you use spin orbital basis false, it will call the spin trace code, which already separate the alpha and beta block. So this thing should work out of a box, but it doesn't because the example has some old equations. But not worry about that right now. All right, so let's do Python 3 cc example open. cc example open out. Yay! So actually it runs with the spin orbital version. But now, as you can see, there's a little bit of an issue with the CCSD iteration with spin. And the reason for that is very simple to fix. So let's open the CCSD dot. I think it's here. Yeah, so just in case you're running this example on your own, trying to run this as an open shell, and then suddenly you get that weird error. And the reason is residual CCSD doubles. I think it's this very end.
Oh my god.
Yeah. So in the spin traced version, which Eugene implemented, it's really awesome. Spin trace makes your code like infinitely faster. No, not infinitely faster. Just really, really fast because you don't spend time computing the unnecessary blocks of your amplitude equations. This is just a very simple mistake, but I think this is coming from like a very old build probably, and I think Eugene fixed it. So just have to pull it.
So wait a second. I made the example, and there was a bug, and I fixed the bug, but I didn't fix the example. That's what you're saying.
I think so. Oh, this is the one that I actually already fixed. So, but I commented out the fix. How should I explain this? Well, okay, we can actually see this because I already fixed this a little bit. But you can see here that this is a two-body integral in sum, right? So this is electron 1, 2, 1, 2. And it should be in the alpha beta block. And so F is alpha, E is beta, N is alpha, and M is beta. But now this expression tries to reorder it or transpose it. So now it becomes EFMN. So it becomes beta alpha, beta alpha. And this is fine because the alpha and alpha, like the alpha still goes to alpha, beta still goes to beta. But now because alpha and beta does not have the same size, like it's just a mismatch. But I think if you run the CCSD code gen, this is fixed. this is not fixed in the example. So right now, just for the purpose of running this example, I'm just going to transpose this. So I will turn it back to FENM ordering. Yeah, I'll make sure I do the proper substitute of all the equations using the code gen, and then I'll push the fix. Oop. Okay, so let's rerun this. Yay! So now it works. Both example matches the energy I got from the Cipher running CCSC, and I believe this is timing. So you can see that this is the equations in terms of spin orbital. It takes 1.6 seconds. If you do spin trace or spin integrated, it saves about 25%. It's such a small system. But you can see it's faster on my laptop, which is the puny laptop. But it works, yay!
That's awesome. That's surprising that it speeds it up at all for this small example.
Actually, yeah.
Because there's more equations.
This is like, I don't remember if we printed it, but, and just to make sure I'm not cheating. Okay, that's the energy I get from the spin orbital. This is the energy from the spin trace. You can see 295.131.202.76909. Okay, last digit. Who cares? Same number. Cool. So we already extended CCSD example to OpenShell. Awesome. I'll fix that and push it. Cool. So yeah, anyway, this is a very small system. MGF is like, what, 21 electrons in 28 spin orbitals. So there you go. 21 electrons and 7 empty orbitals, spin orbitals. Right.
I'm impressed.
Okay, so now we're moving on to CRCC if we still have people watching.
There are 8 people, including you and me.
8 people. There's already one victim. Oh, Danny had to go. That's right.
Do you want to do the bug report and the PR for anything else, or before you do CRCC?
Oh, that would be fun. Yeah, I've never really done a bug report.
Today's
so
the day.
Do it. Let's go here. I should probably clean the code before a pull request, but we can do the bug report.
Okay.
So I guess I go to issues. Wait, I go here, right?
Yep, new issue.
Yay. Title. So I guess I should use a very descriptive title.
It's recommended.
There is a bug on the Cipher interface example. And then on the, I guess I can say CCSD. So what should I write, Eugene?
I don't know. You know what the bug is.
All right. So let's try to be as descriptive as we can.
Say which file it is and say that it works fine for closed shells, but if you generalize it to open shells. No. What was the problem? When you do spin tracing, it doesn't work.
Yeah, when you do spin tracing, it transposes the indices. Yes. But it's, yeah, I think it's fixed in the code gen, so I think we're fine.
Why don't you verify that it's fixed in the code gen?
Oh yeah, let's do that. I mean, we are here. Okay, so let's Python 3 CCSD code gen with spin. So it's already there. Actually, let's take a look at the file.
That's a great idea.
So, right, so this is just the header. So it's all standard stuff, except for something. I forgot where you actually...
There's the spin map.
Yeah, this thing, right? So now instead of calling fully contracted strings, you add fully contracted strings with spin. And now, well, so this is energy. So energy equation is fully contracted, so like it will handle all the spin contraction in this function, I believe. But now when we're dealing with projections, now we gotta be careful because now, okay, like for example, T1, you excite from M to E in this example, and you want to specify in the spin labels, and you have to give this, you have to make this dictionary. What's the spin label of each index, and then you have to pass it to the fully contracted strings with spin. Right. So you have to do this for external or any uncontracted indices that you have. So that's the alpha block. Then here in the beta block, you have the VEB, right? Right. And then, yeah, I think there's also, it's not a bug, it's a feature. Right now, the slices are still done manually. So you will have to do post-processing to define properly like the alpha and beta slices. I don't know, like, is this updated yet? Probably not, right?
I didn't update it. I thought that's what you were doing tonight.
Oh, no. Oh, that? Yeah, we can do that too. That should not be that hard. I have that. I have already done that. But anyway, you can already see, right, that in the function definition, we're defining the slices as just the alpha, because like if you have closed shell, alpha and beta will be the same.
So
But
in your code, the header only passes O and V. It's not OA and OB and VA and VB.
yeah.
So
So
all
what
you
I
have
did
to-
is
All you have to do is change the header
yeah,
in this file.
yeah. Basically, well, you have to do more because so this is the vanilla. That's not .py, right? So P1AA, for example. Where's this? Singles. Yeah, for example here, T1AA residual. So right now everything is defined in terms of the alpha slices. But that's dangerous. For example, in this case, we will have BB, which is like gonna take the OA and VA, right? But this, I think this is handled in the C++ side,
What
which
is?
I haven't, like, or wherever Nick Rubin's parser is, like generating this expression.
This is yes. So that's on the Python side, and that's why I hard coded it as only the alpha block because I didn't want to mess with his
Okay,
parser.
well, okay, I haven't done that. So I haven't messed with his parser to do that. But the way it's printed, it's very specific. Like it's always AA square bracket, and then OV and BB and so on and so forth. So what you can do is create a script with regex. Grab anything that is AAAA, change this to basically append an A after every slices. Or if it's ABAB, change it to A and B and A and B. So basically that's what I did to make that CCSD with spin work. So I'm sorry for not doing that properly, but
We didn't communicate any of this, so all is well.
yes, this is all done by winging it. Anyway, so that's all you need to do. All right, I should go to that cipher interface. I think that's the file. Okay, so anyway, yeah, so now you can see that here I'm basically just modifying that with a simple search and replace. And you can do that with regex to just search and replace everything. All right, so let's take the name of this function. And in function under examples, and then where's this?
Type 4 interface, maybe.
Yep. Type 4 interface ccsd.py. The how should I say this? The np einsum also flip the indices of electrons 1 and 2. Oh yeah, we haven't run this thing actually. Sorry about that. So let's run this code now. Oop. Oop, there you go. So that's the output. So let's look at T2ABAB. Def. Okay. All right. So here, let's look at this. So now
Yeah,
EFMN stays EFMN, ABAB, so we're good. Yeah. So basically, all we need to do is just to replace that function with whatever this part is here.
And it's only that function? I guess that's the
I
only
think
one
so.
that
I think the
matters.
T3 looks correct, surprisingly. I thought it would be an issue everywhere else.
T3 looks fine, you said?
I think so.
Okay.
Let's just take yeah. Okay. Ooh, Princess D. Yeah, well, this is probably still messed up. No, even the T2 update inside CCSET is correct. I have no idea why.
I probably made the example
Like
at the
before.
very beginning of working on this, and then
Right.
it was
It looks like it.
bugs were sussed out by the time I made the pull request.
Okay, we can try. Okay, AAB. Let's try. AAB. So now it should be FBB, CD contracted here. So CD are both beta. So yeah. And AB is just alpha alpha, so that's fine. Yeah, I think this is fine. At least from a cursory look. I remember the issue being only on CCSD. So, alright. Running CCSD code gen with pin.py under examples gives the correct np einsum. Okay, guys, if you're
can you
watching
really-
this and you're wondering why I'm very particular about formatting,
It's your training.
that is my PhD training. Yes.
Can you really be sure that it gives you the correct whatever if you haven't copied and pasted that code into the example and see if it runs correctly?
That is a good point. Should we do that?
Yes.
All right, let's do it. Let's see. csv.py. All right. Okay. Ooh, and then we will have to do the reject live. Nice. Okay, that's awesome. Okay, let's comment this out. And then I'm gonna copy CSV code gen. Oop. T2 AB rest. Right, then I think this is the last function. So I can just copy that. Okay, nice. Okay, let me make sure I'm doing this properly. Anything that can stay. All right. Okay, you ready to see me butcher this?
Yes.
Okay, we will do rejects. So, let's do one by one. And then we will do this. OV. Well, this can also be a tutorial in how to use regex.
I don't know how to use it. And from looking at this, I still don't know how to use it.
All right. I think you need to do this. A to A. All right. We'll just butcher this. Don't worry. Hey, that works. All right. Looks well. Okay, so let's go through this example. So the square bracket here is what we call, I don't know, like I don't know what the proper terminology is, right? But basically, the square bracket indicates that anything inside this square bracket is a fair game, like so that triggers a match, right? So I'm looking either an O or a V, right? And anything inside a parenthesis, which I think in VI you have to escape, because otherwise it thinks that you're looking for a pattern parenthesis, is called a capture group. So whatever it is inside a capture group, you can call it back with like in Bash, it's like $1. So this is the first capture group. This is the second capture group. So now I have two capture groups because I want to do a general sweeping search, right? It can be OO, it can be VV, it can be OV or VO, and I just want to append an A at the end of that, basically. Right. So this one line basically helps me shorten the work of doing 4 explicit certainly replace with OO becoming OA, VV becoming VA, OV becoming OA, and VAOA, the other one.
Do you need can you hear me? Do you need the curly parentheses, the rounded parentheses? Does that ever show up?
I think curly brackets in regex means something else, like you repeat a pattern multiple times, for example.
I see. So it's not that you're looking for it inside both a square bracket and a round bracket. It's
no, yeah. So the round bracket is basically just saying whatever you found within that, keep it, and you can call it. And the first round bracket you can call it as 1. The second you call it as 2, and so on and so forth. Yeah. So if we run that, you can see here, okay, it's F, AA, OO, and VV, right? So if we run it, boop. Now it's just OA, OA, VA, VA.
amazing.
Beautiful.
Apparently, this is different than regex in Python.
It is slightly, yeah. Okay, so let's do this. So now we will change all the BBs and AB will just be ABB. Sorry. Oop.
There shouldn't be any AB.
You don't have any AB. Nice. Well, yeah, there's the ABAB, but cool. Oh, that's true. Yeah. What am I saying? I don't know what I'm doing.
Listen to yourself.
All right, so now so we're done with all we're done with all the one body quantity. So now let's move on to the two body quantity. Woohoo! So now I just have to copy this. Oop. Oop. Right, so now we have two indices. And now I think we just have to do that, right? And don't forget this. So now, let's see, where is an example of AAAA? There is. So for example, here, now it's AAAA. And then let's do ABAB. So I guess technically I could also capture the AB and B, ABAB, and then that would also help me, but that's fine. Okay. Wow, it's amazing. Like, this regex is so easy to mess up, and I expect myself to just butcher this live, and it works so far. So that's pretty nice. Yeah, so basically this is what I did to quote unquote fix the code. And with that, I think we're good to go, because those slices are only important for the orbitals. And as you notice, like, even with spin trace equation, because you already pre-sliced your T1 and T2 objects, like, you don't have to worry about those slices. Like, you will always use the full objects. I think all the...
Now, can I ask you another question that's unrelated to this?
Yep.
In the AAAA T2 update,
mm-hmm.
do those labels get transposed? I know that it doesn't matter in that case, but I'm wondering if...
this one?
No, in the doubles res for AAAA.
Oh, good question. Guess it could be. Let's look at it. EFMN. No, it's not.
It must have been a typo in the spin map or something like that.
It could be something, yeah, silly. But I think that's basically what I did, and yeah. And as you say, like, it doesn't really matter for the all alpha or all beta cases. So I think this should work. So let's rerun. Oh, yeah, we're in the cipher interface. Let's rerun the example again, and let's hope for the best.
Ooh.
Ooh, Python. Okay.
Oh yeah, there's no indent there.
Whoops. There's no indentation. Yeah, I forgot about that. Ooh. There you go.
And wait. Go back.
Oh.
Your doubles res, you have to say equals the first time.
Oh, yes. Good point. Yeah. So as you can see, there are a little bit of funk that we still need to kink out, but it's super awesome. Still works. Hey, works. Okay.
Amazing. Okay, all of that was just to have the confidence to say whatever sentence you had in the ticket.
Yes. So science, I like to make this joke that you can't just double check it. You have to triple check it. It's like couple cluster. You need triples.
It's true.
Very lame, but there you go. Gives the correct anti-Einstein expression with no transpose flip indices. I think that's it.
Okay.
It seems that from a cursory look or search, that this is just a typo in the CCSD module and not found anywhere else. Oop.
Wait.
Oh.
You should add a label that it's a bug.
There you go. We can always edit it. Can I?
To the right, it says labels, none yet. That's probably.
Oh, nice. Label. Uh,
Well, I can see it. I can make it a.
yes.
Oh no, 3 issues?
3 issues?
Labels.
Oh, yes.
Bug. It's now a bug.
Yay. Nice.
Cool. All right, now we all know how to submit a ticket.
Yay. Cool. So, anyone watching, if you're using PWQ, you know how to do that. Now I know how to do that. All right. So now, cool stuff. CRCC. I don't know. Are we still doing this, or what time do we usually stop?
I put in the little stream info that it was 8 to 11. So it's up to you how long you want to go. It's almost 10.
And are you still up for it?
Oh yeah.
I admire your enthusiasm. All right, CRCC.
Oh man, and you have to handwrite the notes. This is gonna be great.
Yeah. All right. So CRCC, right? So
I'm gonna tweet that you're doing this.
Sorry?
I'm gonna tweet that you're doing this now.
I will not do the whole thing that we did with the diagrams, or like the whole CCPQ derivation thing, but I will just go through the expressions. So I will make use of a concept called many-body diagrams here. It's a, how would I say, it's a narrower version of Feynman diagrams. I honestly, like, I don't really know how Feynman diagrams work in general. I just know like its particular application in many-body theories, especially in couple cluster, and actually with MBPT. Yeah, we did MBPT with Piotr. I just don't use MBPT that much, so I forgot about it. But a cool fact is that if you're wondering how a diagram looks like and you're a quantum chemist, or if you're thinking about being a quantum chemist, you can just get this awesome book, Double Oslin, right? And I don't know if you can see the cover. But anyway, on the cover of this book, which is censored, nice.
Yeah. It's not safe for work, I guess.
Yeah, it's not safe for work. Maybe trademark. But anyway, at the cover of this book is actually a many-body diagram. And I believe that is something like a fourth-order perturbation theory contribution in the energy. So that actually brings you triples contribution if you talk about it in couple cluster language. And I think the book actually has some diagrams inside it, so you can read the book and see how diagrams look like. Anyway, I will try to minimize its use because like it will take a whole semester of lecture to even explain how that thing works and relate to second quantization. All right. So anyway, the case that I want to work right now is like, let's start with the normal couple cluster expression, right? So in couple cluster, we have wave function that's expressed as e to the t acting on your reference determinant, right? This is single reference couple cluster. There's also multi-reference couple cluster, which I knew next to nothing about. I'm not going to talk about it. Anyway, so this is typically your Hartree-Fock, or I'll write it down. Hartree-Fock determinant, right? And T is your cluster operator. And as Eugene already demonstrated, this can be expressed as a many-body expansion, right? And you can have single excitation, double excitation, triple excitation, and so on, up until what we usually denote with T capital N. And capital N is the number of electrons. So if you think about it, like, so this guy look like, sorry, Eugene, I will use this notation. So this is my notation for a creation operator, right? And if you can see this is like you can have an einsum expression, right? So sum over I and A. So yeah, basically you have as many annihilators, right, as the rank of your operator. So if you have Tn, so it's gonna look like I1 goes to In, A1 go to An, and then I think should be able to, nice. And then I will have something that's like A1, well, AA1, AAN, IN, AI1. And notice that for the annihilator, you write it in the reverse order. Anyway, so this annihilator, if you put it on phi, then you can see like the first set of the operator, which is this annihilator, they will destroy all your electrons in the occupied space, right? So if you have another rank, which is n+1, you will have an extra annihilator, but you already basically emptied out your occupied space. So this thing in a higher order doesn't exist. So this is not an infinite sum. Right. So yeah, Eugene already did an example of CCD where you only have T2. I think, yeah, so I ran an example with CCSD, which means T contains T1 and T2. Now, what is known is that if you go all the way to like all this, to include all these components up to the component that excite all electrons, you get back the exact, or what is called full CI, full configuration interaction description of your system. It's like the numerically exact solution in a given basis set. Right, but of course that's computationally very, very expensive, and actually doing full couple cluster is kind of dumb because you're trying to do full CI in a nonlinear way, so that's like a complicated way to do full CI. So usually that's why we truncate this expansion, right? But it is also well known that even with CCSD, which has like n to the 6 scaling, like you usually still cannot get a qualitatively accurate result. You will need at least T3 to get something that's reasonable with respect to experimental results or full CI. But then like your method's going to be very expensive. So the question is, how are we going to include the effect of T3 in a non-expensive way, right? So the simplest way is to run CCSD, for example, and then you get like the ground state energy using CCSD, or you can do equation of motion for excited states, and we'll not go into that. Just touch it a little bit, and then to correct, you do something which I will call a delta, and then I will put a function of T3. So somehow we will try to use the T1 and T2 that we solve for, and then build some kind of T3 correction to the energy, right? And then my total energy will just be E of CCSD plus the delta T3. So in practice, there's like a lot of ways you can do this, like a zillion of methods. You can also turn to other alternative where you can just do some T3 iteratively, but there is a very like popular method of including this T3 effect called CCSD parentheses T, where you use arguments from perturbation theory to build this T3 correction. But now I will not look into that. I will look into a series of methods called CRCC. In particular, we'll look at a method called CRCC23. Gain, so the energy is just E of CCSD, and it has a correction 2-3. And this correction 2-3 is actually not super complicated to build if you know couple cluster. I guess that's the caveat. Right. So I guess before we do that, let's think about how we are actually solving for CCSD energies, right? So in CCSD, your wave function. Oop, not gonna do that. Ooh, don't do that. There you go. So in CCSD, your ground state wave function is e to the t1 plus t2 acting on a reference, right? And first you solve for the t1 and t2 amplitudes, right? By solving projection on singly excited and doubly excited determinants. So this is how we denote singly and doubly excited determinants. And
I don't think we defined H bar.
Yes,
Oh, you're
that's
going to do it.
exactly what I'm writing next. So it's just e to the minus t1 plus t2 h e t1 plus t2. Right, so that's your similarity transform Hamiltonian. So you truncate that and you zero this. So if you solve this equation, then your energy is always going to be your expectation value of h bar relative to the reference determinant. This always gives you that after you solve for T1 and T2 amplitudes, right? So, if you see these equations, you can also think, well, what if I play with this quantity? I, J, K, A, B, C. Okay, that's a weird way of writing from right to left. But basically, this quantity, okay, do you want to guess what this is going to be?
Me?
Yeah? Is it 0?
No, it's not 0.
It's not 0. Yay! Because we are not enforcing that this quantity is going to be 0.
Ooh, Marcus went the other way.
Sorry?
Marcus went the other way and predicted 0.
No, Marcus, it's not 0. Yes, exactly. Because h bar is only solved for T1 and T2, right? So this quantity is what we will call moments. And let's call it M3 just for easy. So this is M3, and this is what's going to go into the correction, right? Ooh. All right, so now for the actual correction itself, it's actually pretty straightforward. Let's just call this I should probably sum over. And okay, if I want to do this properly, let's just do this 1/36 because I don't want to think about ABC. So we will be summing over all these little IJK ABC projections, and then we will do this thing called L. IJK. Sorry, this is the excitation. So IJK ABC. I'm kind of mixing up sum notation and explicit summation just to make sure. Over D IJK ABC. Cool. So okay, we kind of figure out what this is. So now what the hell is the LIJK ABC and DIJK ABC, right? And actually, if you're into couple cluster theory or you're trying to learn, a lot of the time, the triples correction is gonna have this kind of structure where you have some quantity on the left, on the right, you contract them, and you divide by a denominator, right? And parenthesis T correction looks exactly like this. It's just that L, M, and D looks different from what we will have, right? So, okay, so we figure out M3 looks like that. So L3 or LIJKBC is actually gonna look similar to this, but you can imagine like the complex conjugate of it. So now we want something like that looks like this. H bar B I J K ABC. That is kind of your first instinct, probably. But there's that thing where we said before where H bar is not Hermitian, right? So this is not something you want to do. Actually, what you want to do is do this. 1 plus lambda 1 plus lambda 2 H bar. Ooh, and what is that lambda? Right? So, okay. So lambda is an additional operator that we introduced because H bar is not Hermitian. And as Marcus said, this is the excitation operators. So oops, where's my cursor? Right. Well, so if you remember Eugene's notes that before we do this, you actually have like which is what we call the connected cluster form of the Schrodinger equation, right? Is E0 P, right? But now if we want to do couple cluster from the bra side or for the left side, it's not gonna be as simple as saying like, okay, now I'm just gonna do this. H bar is this. E0. This is not true, basically. So instead, we will start by parametrizing the left wave function or the bra wave function in a weird way. So we will introduce this 1 plus lambda e to the minus t. And you can't do it the other way around because this and this operator, they do not commute. So lambda is a D excitation operator. And you might be wondering, why are we using D excitation operator? Well, if you write like an excitation operator, let's just do, I don't know, T. Let's say T1 is TIA, AA, AI, right? And what is T1 dagger? Basically gonna be TIA star. And then when you're daggering or when you're doing a complex conjugate of this, then you have to revert the ordering of the operator. Right? And it looks like that. And you can see that it destroys electron or annihilates electron in the virtual orbital and creates electron in the occupied orbital. So yeah, if you're thinking about, like, for example, acting on the cat, right? It acts as a de-excitation operator because it moves the electron from a virtual to an occupied orbital. So like it moves the electron down. But if you think about it from the bra side, it actually excites electron to the left, right? So basically, if you plug this into the Schrodinger equation, H and do a certain manipulation, like, okay, 1 plus lambda e to the minus t h, and then you can multiply from the right now by e to the t, and then you can have this. Sorry, this is reference determinant. 1 plus lambda, e to the minus t, e, and then I can just put e to the t because they are just numbers. E is just number, sorry. This is 1. This is h bar. So you can see that now my left eigenvalue equation looks like this. H bar equals v 1 plus lambda e. Right, so that's the fundamental equation for the left-hand couple cluster equation for the ground state. Right. So anyway, all that just to say that you have to solve for the lambda 1 and lambda 2 amplitudes, which corresponds to the left CCSD equations, right? And then you form the projection of the left CCSD equation with h bar onto triply excited determinants on the cat side. So you can think of this as like the conjugate of M3, but within the EOM or within the non-Hermitian formulation. Now, like, you have to add this 1 plus lambda 1 lambda 2 equation.
Marcus asked if you would ever use an exponential form of lambda. 1 plus lambda.
Exponential form of 1 plus lambda. Like, you mean for the left? I don't think so. I don't think so. You could use a different form of couple cluster, like unitary couple cluster, I guess. That kind of counts. Because then your bra is a conjugate of the cat. But I don't recall anyone using this. There's a variational relaxation since you truncate lambda 2.
Well, I guess, yeah, that would be... the bra wouldn't truncate if you had an exponential exponential form of lambda, is the reason.
Yes. Yes, that's one of the reasons why we are doing this projectively, right? Because we try to form an expectation value with e to the t v, and it's not truncating. But anyways, it's probably also related to what you did, Eugene.
What I did?
With the RDM. I mean, not in the stream. Because you were playing with that RDM thing.
Oh, well, now the whole world knows.
Yes.
I was trying to implement couple cluster as an RDM theory.
Yes.
Because it is an RDM theory.
RDM. Yeah, the energy only... Yeah. No matter what level of truncation that you use. Actually, that's a fun fact. If you go to like all these codes, right? And then like you run any of the higher order method, and then I don't know, you look at this, and then you look at the energy equation, right? And even though T contains all the way up until T4, your energy is only going to depend on T1 and T2. So that's kind of one evidence that points to the fact that couple cluster is more closely related to RDM. This energy is contained in 1 and 2 body RDMs. Anyway, that's a tangent. Okay, so we figure out the shape of, or we figure out the form of M3 and L3. Now, the only remaining thing is
Wait,
T3.
I have to interrupt you. Can't you write down... You can write down a projected form of full CI, and then the energy only depends on C1 and C2 as well. But that's not an RDM theory.
Ooh, that's a good point. but
Or
you
it
don't.
is an RDM theory.
Maybe. But you don't solve full CI projectively, though, right?
But you could.
True.
I have CISD codes in Sci4 that I solve in that way.
Ooh. Okay, I should be careful with my statement then. Yeah, that's true. You could do that. Huh, that's right. All right.
All right,
Okay,
focus. You're running
uh,
out the clock.
yeah, we're already 10 p.m. All right. Well, anyway, I'm just gonna write down this expression then.
So
D3 is
wait,
E0.
before you go on, could you give like a physical motivation for why that correction has that form?
Oh
LM over
yeah,
D.
that is a good question. So this is the example that my PhD advisor really likes to use, and at some point I should just regenerate this curve myself. So F2 using the CCPV TZ set. So how does F2 look like? Lewis Lewis picture looks like this. Ta-da! Right. So you might think like, well, I'm just breaking a single bond, like it basically like you just have two fluorine atoms, like that. What the big deal, right? It looks exactly the same like breaking H2 single bond. There should be no weird stuff. Now, if you draw the potential energy curve, well, I need in E, R. So let's draw the energy as a function of the bond length of F. So you can think of like a Morse potential, right? That's the exact potential energy curve. And I think if you run CCSDT, for example, you should be able to get something that's pretty close to experiment in terms of, like bond net dissociation energy, equilibrium bond length, and so on. If you run CCSD, so let's maybe use a different color. I think you will get something that will look like this. So it will overestimate your bonding energy. If you run CCSD parenthesis D, it will look something like this, and then at some point it's gonna do this. Ooh. That's why I picked the rainbow color, because it's trippy. Marcus, don't say that. Anyway, so parenthesis T will often have this issue where you cannot physically describe a bond breaking. And, this is a single bond, right? And you can imagine that this is just going to be even worse if you try to break double bond, triple bond, or break two bonds at the same time, like in water. And that has been observed, right? So what the CRCC23 thing does is, amazingly, it does something that looks like this. So it has, as I mentioned before, like the equation, the total structure looks very similar. There is an L, an M, and a denominator, but it's able to break bonds properly.
I mean more like if you look at square bracket T, that is just like fourth order perturbation theory. That's where the expression comes from. Where does the expression come from in CRCC?
On the expression, right. So when you didn't mention fourth order, so that is referring to MBPT, or many body perturbation theory, right? So like this, basically like, okay, let me rewrite this delta 2,3. Again, it's 1/36 L3 M3 over D3, like sum over like all the contributions, right? So in like parenthesis T, bracket T, this L and M contributions are intuited, I guess, using perturbation theory. And you basically just go order by order. And you just hope that at some point you just include enough terms and it will converge. But because it's perturbative, then in cases such as this, actually breaking a bond is you can't really treat it as a perturbation because it's a huge change in your electronic structure. Right. So in the case of CRCC23, this is actually not coming from perturbation theory. This is derived from something called asymmetric energy expression, where, let's see, delta E is like actually projection of full CI wave function. Right, and then what do I put here? H, and then psi of your couple cluster, which can be truncated. And then it has this form, basically. Yeah. So you can see that if you... Now, this is H, not H bar, so it's Hermitian. So you can act it on the left or the bra side, and you get full CI energy, right? And then the denominator takes care of the overlap, basically. So you're trying to bring an energy that's... You're trying to project full CI onto CC from the bra to the cat side, basically. Right, you're trying to capture that. And this is much more robust than trying to build, like triples, quadruples, and so on using perturbation theory argument. Yep. Is that what you were asking about, or?
Yeah, basically.
Yep.
And then, so you take the triples term is the most important contribution to this.
Yeah, in terms of
delta E.
CCSD, right? Like.
Okay.
Yeah. Well, I think it's not the most. Yeah, I mean numerically, usually it's the most important, definitely. But it's more that you can just parameterize your full CI wave function. In this case, that's how we end up with the L3 component, right? And you can build order by order. And you can just build all this correction from delta to 3, and then you can plus delta to 4, plus delta to 5, and so on, basically. And it actually will stop at delta to 6. For reasons that it's going to take too long to explain now. But yeah, basically this form of the correction also stops naturally. Anyway, so all right, let's look at the denominator again. So this is just this IJK ABC H bar E IJK ABC. So you can think of this as an expectation value of H bar between two triply excited determinants. It's like the diagonal of the matrix. Right, so we basically have all the components that we need here. And we can now plug it into P-Dagger-Q to generate the working equations. I haven't tested it, so we'll probably just stop after we generated the equations. Right, and as you can see, like this is probably going to be horrible if you try to derive it by hand. I think I tried it at some point and I just gave up. It's that horrible, even with diagrams. So I have here.
CRCC cogen.py.
Yes. So once I tested this and make sure that this works, I'll also push this. So I'll probably do 2 pushes, one for the open shell and one for a CR. Or sorry, pull request, not push. Right. So basically same thing, but now we want to do projections of H bar reference onto triply excited determinants, right? And this now H bar contains T1 and T2 only. So now let's set the left operators to triples. So we have E3, IJK, CBA. And then we add similarity transform, one two-body integrals with T1 and T2, simplify and do that, and then we just print it, right? That's your M3 component, and that's exactly this. You do reference H bar projected on IJK-BC, right? And this will give you M3. And then for the left moment equations, now we need to set the left operators as 1 plus lambda 1 plus lambda 2. So you can set that by using 1, L1, and L2. And I'm going to double check this with you, Eugene. I think I have to separate 1, L1, and L2 with their own square brackets, because otherwise it will also add like product terms.
Yeah, so there's the outermost square bracket denotes a sum, and then the inner ones denote products.
Yes. So, like for example, here in similarity transform operator,
it's different in that function. In the set left and set right.
So if I
you have a product, that would be the product of the three.
Yes.
Yeah. I can't remember why that functionality is there.
That's probably useful for unitary couple cluster.
Every functionality that's there is there for a reason, so it's useful for something. Yes. I just can't remember what.
So that's a sign of good code, that everything there is there for a reason. If you look at my code, it's gonna be something else.
Yes, it's probably for non-particle conserving. UMCC. Because yes, so you can.
Oh, right, like use the single creation annihilation operators.
Yeah, so you can define a bra state as a product of a creator and two annihilators or something like that.
Yeah, like odd numbers of operators. Yep.
Thanks, Blue Density.
It's Marcus.
I know.
Anyway, so now we are projecting the left wave function to the right, right? So now the right is the triply excited determinants, and we put E3 on the right with the other. Now it's like create on ABC, destroy on KGI, right? And now just in terms of the implementation later, this will have to take L1 and L2 amplitudes as well, so don't forget to do that. And same thing, there you go. So I think this will take like a lot of time. No, this is not that bad actually. Ow. Boom.
This goes back to, this code is not the ideal way to implement something like this, but it works and the interface is clean.
Yes. It's awesome though. I haven't even gone to the diagram part. But so with diagrams, so Eugene mentioned, right, that P-dagger Q is based on second quantization, but it doesn't really use Wick's theorem, right? Like we're just using I haven't even contributed anything. P-dagger Q just uses...
You contributed a bug report.
Yeah, that's true. The anti-commutation rules, right? But with diagrams, like a lot of the anti-commutation that will just give you 0 is taken care of. And like I will show a very short example as a proof of concept. Oh man, this is taking forever. My laptop is too slow. That's fine.
Anything with triples takes a couple minutes.
Yes, it should be shouldn't be that bad. And as you can see, I actually already generated the output. I'm just too lazy to open it. Anyway, so with diagrams, you can just simplify all this, right? But even with diagrams, if you do it by hand, it's still like a tedious work. I had to derive left CCSDT by hand. Took me just a few months, I think.
Oh my god.
No, actually, no, that's not true. It took me 2 weeks of nonstop working on that. But still, that's too long. With PDagger Q, as you can see, it's just like done, few seconds. And it's actually useful because I can double check whatever I generated, right, by hand with this. So it's really awesome. So yeah, now you can see that it generated the equation, and we can actually just plug this in. But I haven't written the driver, so it's too late to do that now. All right. So now M3 and L3 are taken care of. So let's check this, check, and check. So the last component we need is D, right? And now here we see that we just need the energy basically, and then you subtract this diagonal elements of H bars between triply excited determinants.
Can PDagger Q even do diagonal elements of a matrix like that?
It cannot.
So how do you handle this? I guess
Tested
you're
it,
about to show us.
So I have to do it in a very hacky way. All right, so I'm just gonna take a closer look at this, but you can see that I'm doing this in a very hacky way, but this is actually useful for also building H-bar elements and intermediates. And I'm kind of mixing my own way of thinking using diagrams with PDagger Q here. So, okay, just a short detour with diagram. So, if I want to represent triply excited determinants in a diagram, I'll use a dot with 6 lines. And it has an arrow that goes back and forth. And I will label them with I, A, J, B, A, C. And then on the other side, it also has this. Yes, Marcus, it's back in time. I know that. This is I, A, J, B, K, C. Right. Yeah, like if you're watching the stream and like you have no idea why Marcus is doing that, I basically gave a lecture about this like last year, and what, like it took like 2 sessions, 4 hours each, or something like that. It was like, whoa, the concept is just so weird if you're not used to it. Anyway, and anytime you do something like, something like this, then you read it as a Kronecker delta, right? So if I have 2 different index, then like it's a Kronecker delta between 2 different indices. So now, as you can see, if I put a diagram called H bar in the middle, so Hamiltonian, our electronic Hamiltonian has 1 and 2 body contributions, right? So in diagrammatic terms, that means you will have parts that have 2 lines and 4 lines. So you can already kind of intuit that each line kind of correspond to 1 index in your tensor. Now, so a T1 operator, for example, has I and A in it, so it's going to look like that. A T2 will look like that. I, J, A, B. Okay, just roughly speaking. And the directions has meaning, right? But anyway, for the purposes of this, I'm just going to say something and you can take it at face value. I did my due diligence. But this expectation value, you need H bar that has one line going to the right and the left, two lines that goes to the right and the left, and lastly is three lines going to the right and the left. And if you try to do 4 lines, there's no such thing, basically. Right. And then you can form various contraction, and you will see that you will need 3 indices on the left-hand side, 3 indices on the right-hand side. And the remaining 3 indices has to match between the 2 triply excited determinants. So they will form another set of delta. Right, so basically I will need like H bar something that looks like II and H bar AA. This one I will need something that looks like IJ, H bar IA, and H bar AB. And for this one, I will have something that's going to look like IJA, and H bar IAB. So you can take my word for granted. If you're interested, you can try to derive this on your own, or use Pythagoras Q.
Why don't you have IJK?
Because of the structure of the Hamiltonian. So like, well, actually Pythagoras Q will tell us. Well, no, Pythagoras Q will not tell us, but no, you will not have IJK. We can code it, it will give you 0.
Okay.
Yeah. Actually, that's a fun experiment. Let's do that. This one is like simple. But now, to be able to do that, as you can see, now I'm setting the left and the right operators using just this like single creation or annihilation operator. And you have to know what you're doing, basically. But to make sure you are doing the right contraction, if it's occupied on the left, it has to be a creation. If it's occupied on the right, it has to be an annihilation, and vice versa. Or, well, and it's the other way around for the virtual index. So for the virtual index, you want annihilation on the left and creation on the right. And then here, I actually do a little bit of a hacky thing. So first, I let Pythagoras Q simplify this expression. And then I know that Pythagoras Q will actually generate a whole bunch of expression with delta in it. So for example, it will create a term that has delta ij, because the I and the j itself can contract, but I don't want that. I want to keep the ij labels. So I skip that, any of the term that has a delta in it, which will print something like D parentheses, basically. And then, so if there's a delta, skip it. Otherwise, put it in the actual terms that I want. And then, that's the expression that I will process and generate. Yeah, so, and then this is the fun thing when we are, so I'm writing this as a function. And this gives me a 2-index object, right? But in fact, I only need the same index, because like, you know, imagine I have IJK on the right, IJK on the left. If I have one operator to contract with the right and the left, I'm basically left with 5 remaining operators from the determinants itself to contract, right? And the indices have to match. So that means the H bar element that I'm grabbing has to have the same index by process of elimination. If that makes sense. So I only need the element that has like II type. So I don't have to store like all of the, like an n square type object. I only need like n. Same thing here with the AB. If there's a delta, just skip it, and then
I'm confused.
Again.
I'm confused about skipping the delta though, because you want just the diagonals, but the delta should still contribute to the diagonal, shouldn't it? If I and j are equal to each other.
Yes, but it's INJ. It's the delta in the full list of triply excited determinants, right? Like if I have E3 on right and E3 on left, that would be in the case. Then like I will just store everything. But the way I'm doing it is I'm just so if I go back here, like I just want to know that element. Right? Like I will code the entire denominator like manually after I obtain each of this expression.
Okay.
Yeah. So this is a very hacky way of doing this. Because believe it or not, I did try using like E3 on the left and the right with the same indices, but it broke the code.
Yeah, no, it doesn't work if you have repeated. So a lot of the logic in there is involves figuring out if something's summed index or not, and it figures that out if it appears more than once. So if you have a non-summed index that you're specifying here more than once, it interprets it incorrectly.
I see. Yeah. And I think I want to avoid doing the other way around where I have like 12 indices to keep track.
Yeah.
And then reduce it to the diagonal at the end. Because that's gonna be
This
amazing.
actually works though?
Good question. I think that should work because that's how the EOM-CCSD Hamiltonian was coded. Like you have 8 index and then you reduce to 4 index at the end. Or like, yeah. But I don't know how my laptop will handle it. So we can try that. That's gonna be not fun for my laptop probably. Keeping track of a 12 index tensor. Anyway, now for the two body, like you just go with the same logic, right? Just make sure you have 2 operators on the left, 2 operators on the right. And this is the reason why I don't want the delta, because this will also produce something that's like, oh, contract like I with K, and then I end up with an element that only has 1 operator left to contract on the right and on the left. So that's why I removed the delta. And that. And that's for the 3 body. And now, Eugene has a very good point. Why don't we have like IJK or ABC? So let's try that. So let's make this, I don't know, like IJK and hope for the best. IJ. Okay, and then, oh, how far can we go with indices?
I think LMN would work, or MNL, however you want to do it.
N. All right, so let's hope that works. So here I have I, J, K. Okay, if this works, then like, I guess you shouldn't trust me. Right. So this will be I, J, K, L, M.
So the reason that he's asking about the labels is labels P, Q, R, and S are general. So the code will assume that they should span occupied and virtual. But I, J, K, L, M, N, and O, I think, are all occupied. A, B, C, D, E, F, and G. No, not G. Are all virtual. But as Blue Density is saying, you can use anything that starts with an I is interpreted as occupied. So you could do I1, I2, I3, I4.
All right,
And then there's
so let's do this. So, okay, so now I set it up so that it's let me think, IJK, yeah. So it should be creator on the left, annihilator on the right. Just double checking. Yep, okay. So, let's run this code. Oh, okay, let's not do fancy stuff. Out. And this is like small contractions, so I think they're gonna be fast.
You thought wrong.
Oh yeah, I have other processes open, so. Well, I still have to rerun it though, because yeah, there you go, proof of concept. There's nothing.
There's nothing. Okay.
Yes. And yeah. And the reason for that is because yeah, you will not have the proper slices of your integrals to get IJK. And also the T amplitudes. Actually, sorry, yeah, forgot. If the T amplitudes, because T amplitudes are because T are excitation amplitudes, so you will have to have at least like a pair of excitation.
Okay.
Otherwise, like it will break. Anyway, so now you can see this greatly simplifies how much thinking I have to do, because now it gives me like, okay, I just need the II, right? So it gives me that IJ, and then like just complete that. There's a little bit of a sign issue. Like you kind of want to double check if you get the correct sign from doing this. I think if it is producing this, then I don't have to mess around with the sign. But I have to be careful with how I coded the denominator. Anyway,
So wait,
I basically can just sum over all of this.
is this the sign issue? Is this a problem with P-Dagger-Q or a problem with how you're defining what your bra and
It's
ket
a
are?
problem with how I'm defining the thing. Yeah. So with dagger Q, I can always like set the equation such that it gives me the proper sign. Yep. So yeah, that's what I expected. So for example, okay, right, like one body, probably that's easy. The two body, it's like, okay, it starts to get more complicated. Like, I don't know what to think about this. Yeah, three body, actually there's only one possible answer to the three body contribution. Right, so basically all that's left for me to do from this point on is to get the driver working.
Sorry, I was answering Marcus.
That's fine. Yeah, but I mean, you know very well that in order to do this, we need to generate the lambda 1 and lambda 2 amplitudes. So actually that's easy because it's already in this. Woohoo! So you can just run this lambda singles and doubles code gen and they will give you the expressions. And I think I am halfway working through it. So
But man, then you need
60.
to solve T equations, lambda equations, generate L3M3, your denominator.
Yes.
It's a lot of stuff to stitch together.
Yep. So I kind of already do that. So here I already put lambda singles and I already put lambda doubles. Yep. I already put lambda doubles basically. And then I think I have the lambda, the driver or iteration. I forgot. Yeah, there you go. Lambda CCSD iteration. So now you need T1, T2, L1, L2. It's just a copy of of the CCSD driver because the way you solve the lambda equation is basically the same for the ground state. You just have to work with the left equation. So now I'm calling the singles and doubles projection on the left. Sorry, on the right. I just have to make sure that all of my objects are shaped properly for lambda. And then like, yeah, basically this should spits out like converts L1 and L2, and then pickety boom, just plug it to M3, L3 denominator, get your energy correction. That's the part that I haven't done.
Awesome.
Yep. So there you go. So in summary, CRCC23, it's very easy to code with pDaggerQ. Don't do this by hand.
Well, I mean, it's easy to generate the expressions, but you still have to hooking it all into a full workflow is not trivial still.
Yep. So first, do CCSD, get the ground state energy, and then T1 and T2, and then do lambda CCSD. You get your lambda 1, lambda 2, and then you compute delta 2-3 equals whatever, L3 M3 over D3. And then, so the energy of CRCC23 is just CCSD plus delta 2-3. Done.
Easy.
Easy. No, it's but yeah, there is a hacky way, right? And actually, I should probably mention that this hacky way of using like the denominator code, this is actually pretty useful when you're trying to factorize the CCSD equations, because you will have, in diagrammatic language, you're basically trying to get diagrams that have lines to the left and lines to the right, because the lines to the right is what can contract with other T amplitudes, or T operator. So that's a very useful tool that you can use to get the working and factorize equations.
Yeah, so I've always just relied on the fact that like it spits out the equations, they are what they are, and then you can just implement them. But the way you're defining your denominator, you could evaluate elements of H bar and like implement equations how you find them in the literature when they're in terms of H bar.
Yes. So like if you know what you want to do, this is a very useful and powerful tool, definitely.
Cool.
Oh, cool. Yeah. So I don't know, maybe at some point I can play around and show the final working CRCC23 code. And another thing that I've played with this type 4 interface is implement a way to use symmetry in a poor man's way. So that will also be fun for EOM, for excited state calculations.
Cool. All right, do you want to play a video game for the next 12 minutes?
No.
Lame.
You can play a video game.
No. It's way too late. This was really great, Stephen. Thank you.
Thanks. Well, thanks for bearing with me on this live coding session. I didn't really code anything. I prepared stuff.
You cheated.
I cheated. Yes. But yeah, that's a good question though. Like, why don't we have IJK? Oh.
One nice thing about pDaggerQ is you don't have to be smart. You just put in the expression, and if it's 0, it ends up 0.
Yes, that's a very good point. It's pretty black box. Yes. Yep. It helped me write my. I think I mentioned this, but it helped me write like my dissertation because I had to do CCSDT RDM.
Yeah, I remember.
And the equations are not published anywhere, so just derived it by hand, checked with PyThagoreQ, and I think I noticed several mistakes that I did. I was like, nice.
All right.
Oh. DILY in the XOR trick
Speckled
works.
lemon. We didn't even go into why it actually works. We should do a
Yeah,
we should do a whole stream on just how cool XOR is.
That's true. We should.
It's so cool.
Yes.
Can you show it off the top of your head?
Like just numerically?
Like on your little tablet thing.
Oh, XOR? I mean, like just make a table of XOR?
Yeah. For
Okay.
like C2V.
All right. Cool. We can do that.
You have a
Yeah.
PhD already. This is not a test.
Like one of the best paper that I'm super proud of is all like it all relies on this table, so I'll be doomed if I don't know this by heart by now. Okay, let's do B1, B2. Let's do this table. Woo! So this is totally symmetric, so A1. So all the diagonals are going to be totally symmetric. So because I started from the diagonal, you can already see why XOR will work. And A1 is identity.
Not all of us are geniuses who can just do XOR in our head.
Well, yeah, sure. And then, okay, A1 is identity, right? So it's just gonna give you the same on this column. And then basically you just have to fill in the rest, and the B2 in this case is gonna be your what do you call this? Like this is diagonal. What's this? The other direction?
Off diagonal.
The other diagonal.
What?
Like the other diagonal, like the
I
B2.
don't. This is a question for Marcus. I don't know the name for that.
Marcus, what's the thing that's orthogonal to the diagonal? It's still diagonal. Anyway, this is P1, P1, P1 times P2 is A2.
I don't think I
B2.
ever noticed that that's B2.
I think this is arbitrary. Like you can also make the table.
Yeah,
like,
sure. Depending on the order. Yeah.
Yeah. Oh, this is a fun fact. Like you probably know, but if you have the U and G symmetry, like you should show your tweet about the UG.
I should.
Because it's just perfect for that joke. If you have the U and the G, you have to block the G and the U's together.
Say again. Sorry, I had just gotten your joke and.
Oh, yeah. Yeah, so like some code will do like AG, AU, and then B1, G, B1, U, right? Like that will not work with the XOR.
Oh,
anyway.
Interesting.
Sorry?
Interesting.
Yeah. Anyway, let's do an XOR table. So, binary XOR is... Okay, XOR. So if I have 0, 0, exclusive OR. So this gives me 0. Right? 0, 1 gives me 1, 1, 0 gives me 1, and 1, 1 gives me 0. All right, so let's do XOR table for 0, 1, 2, 3, which is going to be 0, 0, 0, 1, 1, 0, and 1, 1. What's that? Off diagonal. Okay. Anyway. 1, 0, 1, 1. All right. Okay, so let's look at this bit. 0, 0, 0, 0. That's going to give you 0. 0, 0, 0, 1. That's going to give you 0, 1, which is 1. 0, 0, 1, 0. That's going to give you 1, 0, which is 2. This is, you can expect that's going to be 3. And this is a Hermitian matrix, so you can do that. Awesome. So now, you can see that the diagonals, they always have the zeros and the ones at the same bit. So it's gonna give you 0, 0 or 1, 1. So it's always gonna be zeros. Aha. And you can already see that this is gonna give you 3 because it's gonna give you the 0, 1 and 1, 0 type. So it's gonna give you 1, 1. This is also 3. And this is gonna give you 1 and 1 and 2 and 2. And if you map 0 to A1, 1 to A2, 2 to B1, and 3 to B2, you get the exact same table. And
Amazing.
that's very useful for, yeah, keeping track of symmetries.
But it only works if your point group is abelian.
It only works if your point group is abelian, yes. Should mention that. But actually, yeah, is there any like practical quantum chemistry code that handles non-abelian symmetry?
I think there are codes for Hartree-Fock that do like D4H and.
Oh yeah, I mean I did run it.
I don't
Yeah,
know how
Games
they
has
work,
it.
Do you know how they work? I don't know how they work. I know how abelian symmetry works, but
Yeah, I have no idea. Anyway, yeah, that's a pretty cool trick. So yes.
do you know who first came up with this or first noted this? I asked Twitter a long time ago, and I can't remember the answer.
I have no idea. I have a friend who came up with this independently just by doing group theory.
Really?
Yeah, and then he brought it to Evangelista, his advisor, and then he was like, "Oh yeah, this is known since like way back."
It's in. That's how Daniel Crawford does it in Sci4. There's in C++. It's the caret operator, and so there's carets everywhere. And it took a very long time for me to understand what was going on.
Anyway, yeah, it's a pretty nifty trick. But yeah, like I think if you try to do the same exercise with the D2H, like yeah, it only works if you have the U's and the G's plugged together.
That's interesting. I didn't realize.
Like yeah.
Okay. We've gone. Oh, we have been streaming for 3 hours, even though the first 3 minutes didn't involve any content. So I think I'm going to call it here.
Nice.
Unless you really have anything else you want to share with the world.
Nope, not at this point.
Speckled Lemon, you are welcome. I think for my next one, I have a Rubik's Cube solver that I in the last year, rewrote in Python. And I think I'm going to do a Rubik's Cube stream at some point. And then after the Rubik's Cube stream, Marcus is going to do whatever you guys were talking about. Numba? What was it?
Numba.
No, it wasn't Numba. It was something else. Was it Numba?
Yes. That'd be fun.
Yes, it's Numba. All right, Marcus is committed. Okay, thanks everybody for coming. Thanks for everybody who participated in the chat. This was a lot of fun. And thanks to Steven. Great job.
Thank you.
All right, bye everybody.
Bye.